In episode 1, we built a qubit, and in episode 2, we glued qubits together. But so far the state has mostly sat still. Now we put it to work, and the tool for that is a circuit. A circuit is nothing exotic. Draw a horizontal wire for each qubit and place gates along it, left to right, in the order they act. Time runs to the right. The wire does not carry electricity. It carries the state, that array of complex amplitudes, and each gate it passes through is one of the little matrices we built in episode 1, multiplied in, one gate at a time. The circuit we will stare at today is about the smallest interesting one there is. Read it like a sentence. First a Hadamard, then a phase gate, then another Hadamard.
So a circuit is really just a list of gates in order. That seems almost too plain.
It is exactly that plain, and the code says so. You make a circuit on one qubit, add a Hadamard, add a phase gate, add another Hadamard, and run it. 5 short lines, and every one of them is a real operation on a real array of complex numbers, the same NumPy array we have been carrying since episode 1. Nothing is hidden behind the diagram. But here is the honest question: why these 3 gates in this order? Because together, they do something a classical circuit cannot do at all. They interfere. To see interference, we need to see the state. So let me draw it the way we will draw every state for the rest of the series. 1 bar for each basis state. For a single qubit, that is 2 bars, one labeled 0 and one labeled 1. For the 2-qubit register of last episode, it would be 4. The height of a bar is the magnitude of that amplitude, how much of the state lives there. Square it, and you get the probability of seeing that outcome. And on top of each bar sits a small arrow. That can point in any direction, like a tiny compass needle. That arrow is the phase. The angle of the complex number. Look at these 2 bars, the exact same height and yet different states, because their arrows point different ways.
But if the height alone carries all the probability, why should the arrow ever matter? I cannot measure a direction.
You cannot, not in a single measurement, and that objection is the heart of this whole episode, so hold on to it. For now, just watch what a Hadamard does to a qubit that starts as a definite 0. 1 tall bar on the left, nothing on the right. Watch the tall bar split. The Hadamard pours half of it into the other slot, 2 equal bars now, each with half the probability, and it leaves both arrows pointing the same way. Equal heights, aligned arrows. That is a plane, balanced superposition, and it is our starting line for everything that follows. Now we do the interesting thing, and I want you to keep your eye on the arrows. Into that balanced state, we drop a single phase gate, the one we call Z. It does not touch the heights at all. It reaches under the second bar, the one labeled 1, and it flips that bar's arrow to point the opposite way. Watch it turn. Look at the 2 bars now, the same heights as before, but their arrows are opposed. The picture looks almost unchanged, and if you measured right here, the odds would still be 50-50, exactly as before. Keep watching. Here comes the second Hadamard, and this is where the arrows finally earn their keep. The rule is simple. Each new height is built by adding arrows, tip to tail, like little walks on the page. Start with the 0 bar. It collects 1 arrow from each old bar. These 2 point opposite ways, so walk right, then walk left. The tip lands exactly back at the start, and the sum is nothing at all. The 0 bar collapses to the floor. Now the 1 bar. It also collects both arrows, but the rule flips the second one first, so now the 2 align. Walk right, then right again. Tip to tail they reach twice as far, and the bar climbs to full height. 1 bar cancelled, 1 bar reinforced. That is interference, and we arranged it on purpose.
So we started certain of 0, and now we are certain of 1, with no randomness anywhere.
Certain of 1, no randomness at all, and notice that nothing in the middle ever looked dramatic. The heights never changed until the very last step. All the real work was done by a phase, a direction no single measurement could have seen, quietly deciding which bar would live and which would die. A Hadamard, a phase, and a Hadamard turned a definite 0 into a definite 1, purely by cancellation.
Wait, before you go on, take the phase gate out. Just a Hadamard and then another Hadamard with nothing in between. What happens then?
Good instinct to ask, because the answer surprises almost everyone the first time. The first Hadamard spreads the qubit into that even position, both bars equal, arrows aligned. Now, you might expect the second one to scramble things further, or at best to hand you a coin flip between 0 and 1. Watch instead. The second Hadamard folds the state right back. The qubit lands exactly on 0 every single time. The same gate, applied twice, undoes itself. And here is the part to hold on to. It is not that the second Hadamard quietly cancelled the first, as if nothing had happened in between. Plenty happened. The superposition was real the whole way through, and we could have proved it by slipping a phase gate into the gap, like we just did. For the 0 bar, the two arrows arrive aligned, so they add and reinforce, and all the probability floods back to 0. For the 1 bar, the two arrows arrive opposed, so they cancel to nothing. It is interference, on the way out, that rebuilds the original state. And this is exactly the quantum version of the two-path experiment from our opener. Split the amplitude, recombine it, and let the paths interfere. So let us finally pay off that objection about the arrow, the one you raised at the start. It is true, if you measure a lone qubit, the phase is invisible. The probability of each outcome is the height squared, and the arrow's direction drops out of that number completely. Here are 2 bars at equal height, probability 1/2 each, no matter where either arrow points. Turn an arrow all you like, and multiply the whole state by any phase you like. Every probability comes out identical. No single measurement can ever see it directly.
Then why should I care about something I can never observe?
Because a phase you cannot observe now decides what you will observe next. We just watched it happen, so let me replay the two endings side by side. Same 2 bars, same heights. Set the arrows aligned, run the Hadamard, and everything flows to 0. Set them opposed instead, run the very same gate, and everything flows to 1. The relative phase. Between the bars, the angle between those 2 arrows, is what steers the next round of interference. It is not bookkeeping, and it is not noise to be ignored. It is the resource. And that resource buys something concrete, so let me show you the payoff that closes this episode. Hand a quantum circuit a mystery function as a black box. With the right gates, you can write a global property of that function, not into the heights, but into the phases. Of the state, 1 arrow twisted for each input. Then a final layer of Hadamards makes those phases interfere, exactly like our little circuit did. The wrong answers cancel, the right answer reinforces, and it lands on a single basis state you can just read off. The 2 classic circuits that do this, named for Deutsch and Jozsa, and for Bernstein and Vazirani, each learn in 1 query what a classical computer would need many queries to pin down. To read a hidden string of 10 bits, classically, 10 questions, 1 per bit, on the quantum circuit 1. The wrong answers were never skipped. They canceled. Next episode, Grover's search turns that same cancellation into a slow rotation you can watch climb toward the answer.